Hello students, in this lecture number 3 we are going to study about tri-diagonal systems, and we are going to study about algorithm which is used to solve the tri-diagonal system, that is known as Thomas algorithm for tri-diagonal matrices. So basically tri-diagonal systems are the systems where you will see that only diagonal, superdiagonal and subdiagonal elements are present in the matrix, and rest all the elements are 0. Okay, now if you look in this matrix, okay, you will find that f1, f2, f3, f4 are diagonal elements, g1, g2, g3 are superdiagonal elements, e2, e3, e4 are subdiagonal elements, and apart from all these elements, rest all elements in the matrix are 0. Similarly, on constant side, you have R1, R2, R3 and R4. So there is a special approach to solve this kind of a problem. Now, Thomas algorithm is nothing but a Gauss elimination method only. This is a elimination algorithm, and in Thomas algorithm, you are going to neglect the zeros of the matrices which you are not going to change, and the elements other than zeros are going to change using any one of the element as a pivot element. So let us say, if we in this algorithm you will see that only first element, this f1, is not going to change. This will be a pivot element, and rest all elements will change by taking this f1 as a reference elements. So this particular algorithm involves 3 steps. So first step is decomposition. So here in this particular case we have n is equal to 4. There are 4 equations. Okay, so for k running from 2 to n, that is for k is equal to 2, for k is equal to 3, and for k is equal to 4, we are going to have ek is equal to ek upon fk minus 1. That means if you consider k as 2, then we can write e2 is equal to e2 upon f1. Okay, e2 upon f1, if you see this, what exactly it is? E2 upon f1, this particular element e2 is modified as e2 upon f1. That means we are going to use the same philosophy as which we are going to use in the Gauss elimination. Okay, similarly f2 will be equal to f2 minus e1, f2 minus e2 g1. Okay, so f2 will be f2 minus e2 g1. Okay, so when k is equal to 2, f2 is equal to f2 minus e2 g1. Similarly, e3 we can write as e3 by f2, f3 is equal to f3 minus e3 g1, e3 g2. Okay, likewise you can for k is equal to 4, you can write e4 is equal to e4 by f3, and f4 is equal to f4 minus e4 g3. Okay, this is how you are going to write the decomposition stage. Then in a forward substitution, for k turns from 2 to n, rk is equal to rk minus ek into rk minus 1. That means when k is equal to 2, 3 and 4, we can write as r2 is equal to r2 minus e2 into r1. Similarly, r3 is equal to r3 minus e3 into r2. Similarly, when k is equal to 4, we can write r4 is equal to r4 minus e4 into r3. Similarly, so these 3 elements we are going to change in the forward substitution on a constant side. In the last stage is called as the back substitution. In the back substitution, we can write that xn is equal to rn upon fn. In this case, n is equal to 4, so x4 will be equal to r4 upon f4. And for k running from n minus 1 with the decrement of minus 1 up to 1, that means the k will run from 3, 2 and 1. K will be equal to 3, then k will be equal to 2, and k will be equal to 1. So under that situation, what we have is that, let us say k is equal to 3, then x3 is equal to r3 g3, r3 minus g3 into x4 divided by f3. That will give you x3. Then you put k is equal to 2, then k2 is equal to r2 minus g2 into x x3 upon f2. That will give you x2. Similarly, x1 will be equal to r1 minus g1 into x2 divided by f1. So this will complete, this will give you x4, x3, x2 and x1 respectively. So that step is called as a back substitution. So let us consider an example. Okay, so under this example, all diagonal elements are 2.04, or super diagonal elements are -1, and all sub diagonal elements are also -1. That is, g1, g2, g3 are -1, e2, e3, e4 are also -1, and f1, f2, f3, f4 are 2.04, and r1 is equal to 40.8, r2 is equal to 0.8, r3 is equal to 0.8, and r4 is equal to 200.8. This is what the example. So in order to tackle that, first step is decomposition. So for k is equal to 2, e2 is equal to e2 by f1, you will get e2. While calculating f2, you will use the current value of e2 which you just have calculated, and that is equal to, so f2 is equal to f2 minus e2 g1. So f2 here will be equal to, f2 is 2.04 minus 0.49 into -1, so that will give you 1.550. Similarly, you will calculate for k is equal to 3, e3 is equal to e3 by f2. In this case, f2 value you just have calculated, that value you are going to use, so you will get e3. While calculating f3, you will use the recent value of e3. Okay, similarly for k is equal to 4, you can get e4 is equal to e4 by f3, and while calculation of f4, you will use the current value of e4. Okay, so this is the first stage of decomposition. Then next stage is forward substitution. In the forward substitution, you will use the value like r2 is equal to r2 minus e2 r1. Okay, r1 is 40.8, so r2 is 0.8 minus 0.49 into 40.8. e2 value we just have calculated from this side, that you are going to use, that is 0.49, so it will be equal to 20.8. Similarly, for k is equal to 3 and k is equal to 4, you are going to calculate the value. Okay, and decomposition, and after decomposition and forward substitution, you will write the matrix like this. Now this matrix 2.04 minus 100 minus 0.49 1.5 minus 10 0 minus 0.645 1.395 minus 1 0 0 minus 0.777 1.323 T1 T2 T3 T4. On a constant side you have 40.8 20.8 14.221 and 210.996. Now for a back substitution, that is the third stage. Okay, you can write that when n is equal to 4, that is k is equal to 4, then when k is equal to 4, what you can write is T4 is R4 upon F4. So this is the first step of back substitution. This will give you value of T4. You use this value of T4 and put it to get the value of T3. So T3 is equal to R3 into G3 T4 upon F3. So that will give you the value of T3. While k is equal to 2, T2 is equal to R2 G2 T3 upon F2. So that will give you value of T2. While k is equal to 1, T1 is equal to R1 minus G1 T2 upon F1. So that will give you value of X1, or that is T1. So in this case, you can write the answers at the end. So let us consider this particular system. This is also a standard example application problem for Thomas algorithm. Okay, this is a spring mass damper system with M1, M2 and M3 given as respectively. Okay, similarly K is 10 kg per second square for each spring, and Kx1, X2, X3 are displacement of each springs which we need to find out. Okay, so by using Hooke's law on Newton's second law of motion, what we can write is that upward forces are balanced by on every mass which is there in the system are balanced by the downward forces. Okay, and this is force balance. This particular balance will be equal to mass into acceleration. Okay, so let us say x1, x2 and x3 is the displacement of the three different masses which are there in the system. So upward force on mass plus downward force of the on the mass is equal to mass into acceleration. Okay, so Hooke's law will state that the spring the force which is there because of the spring tension, that is nothing but equal to the stiffness multiplied by the displacement. Okay, so these are free body diagrams which we can draw for three masses. Okay, so this can be equated like this, and this particular set of three equations can be written by using second law of motion, summation of F is equal to ma, mass into acceleration. Okay, now by putting m1, m2 and m3 value and k value, you will get this tridiagonal matrix. If you notice that the diagonal elements are 30, 30, 10, super diagonal elements are 20 and minus 10, sub diagonal elements are minus 20 and minus 10, r1, r2 and r3. Okay, so this is equated to f1 g1 0, e2 f2 g2 and e3 f3 is equal to r1 r2 r3. So by Thomas algorithm, we can find that for k is equal to 2 and for k is equal to 3, we will get the value of E2, F2 and R2. Similarly E3, F3 and R3. We will rewrite after decomposition stage, we will rewrite it like this. Okay, this matrix. Okay, upper diagonal elements we are not going to change, only diagonal elements and sub diagonal elements are going to change. Okay, so this is equal to this. This can be written as the product of lower triangular matrix and upper triangular matrix as shown here. Okay, but that is not relevance. We will just implement a back substitution and we will get x3, x2 and x1, which is the final solution. Similarly, we will write a program. Okay, so in this program you can see that the first loop is taking the value of r, the second loop will take the value of f, the third loop will take all the values of g, and fourth loop will take all the values of r from the user. This is a loop for decomposition stage. Okay, this will run from k is equal to 2, k is equal to 3 and k is equal to 4. Now in the forward substitution, the loop will run from k is equal to 2, k is equal to 3 and k is equal to 4, and we will find all the modified elements on the constant side. The third stage of the method is back substitution. So R4 is equal to x4 is equal to R4 upon F4, that will give you x4 value, and this is a backward substitution loop. It will run from k is equal to 3, k is equal to 2 and k is equal to 1 respectively. That it will run backwards, and it will give you value of, first it will give you value of x3, then x2, then x1 respectively, and this is for printing the answer. So this code you can type in a MATLAB in a script file and run it, and to check it you can modify this code for n number of equations. That is, you can give n is equal to any number and you can get the solution. Okay, so this completes the method of Thomas algorithm for tridiagonal matrices. Thank you.